Hi, everyone. My name is Abigail Bodner. I'm a postdoctoral fellow at New York University, and I'm also the executive director of Climate Match Academy. Today, I'm going to be talking about the El Niño Southern Oscillation. In yesterday's tutorial, you learned to subset a small region from a global map. You focus on the equatorial Pacific in a region known as Niño 3.4, which is where the El Niño Southern Oscillation phenomena originates. Although the El Niño Southern Oscillation, also sometimes known as ENSO, originates in a very small region, it is in fact an atmosphere-ocean phenomena that impacts climates around the world in regions much farther than this Niño 3.4 region. Some people on this call may associate the term ENSO with extreme floodings and extreme precipitation, while others may associate it with severe drought. In fact, different places around the world can exhibit very different impacts from ENSO, which is why this topic has been so fascinating and researched by so many. These two maps are showing December through February on the upper left panel and June through August on the bottom right. And what we're seeing here are different impacts from the ENSO, showing us really how global this phenomena really is. Some places we see exhibit cool and wet impacts. This is represented here by blue and green colors, whereas others will have an impact of more warm and dry climates due to the different phases of ENSO. So again, although we are focusing on measuring the sea surface temperature anomaly in the equatorial Pacific, the impacts of ENSO are really worldwide and they are very diverse. In order to really understand what this phenomena is and what are the interactions between the atmosphere and the ocean, I'm going to be using a video by the Met Office. I'm going to just increase the speed a little bit and talk through. So as we mentioned, ENSO is a phenomena that originates in the equatorial Pacific. And this is going to be the region that's focused up by this animation. During normal conditions, the trade winds of the atmosphere exhibit stress on the ocean surface. In this location over here, we see winds that are blowing from east to west, leading to water near the ocean surface that is being basically piled up towards the Western Pacific. This is known as the Ekman phenomenon, also known as upwelling, where cold water gets pulled up from the ocean interior, and that's what we're seeing on this cold blue tongue on the Eastern Pacific. And then the warmer water, the warmer anomaly, is being piled up on the Western Pacific. This warmer pool leads to evaporation and to a lot of rainfall. This is associated with the monsoon seasons, for example, in Eastern Asia. And from the atmospheric perspective, this is known as the Walker cell. And this is what's thought of as normal conditions where the atmosphere and ocean interact as such that this Walker cell is self-maintained. And we can see this warm and cold surface temperature during normal conditions. During the El Niño phase, these trade winds weaken. And what that means is that the upwelling is not as strong as it normally is. And we will in fact see a shift of the warm pool from the Western Pacific into the center of the Pacific, which means that the monsoon season or the rainfall will actually exhibit itself on the middle of the Pacific Ocean rather than in East Asia, which means that will lead to drought in East Asia, and it will lead to extreme flooding and precipitation in South America and Central America. So as you can see here, there are really different impacts. What we're seeing now is we can now try to track the warm and cold sea surface temperature anomaly that are associated with El Niño. The opposite phase, which we'll see in a moment, is known as La Niña, which is when the winds at the surface actually increase. What we can see here is the surface temperature is really oscillating between the two different phases of El Niño and La Niña. Sorry, El Niño and La Niña. So this is now the La Niña phase, and we can see that the trade winds are even stronger, leading to the warm water being even pushed even further closer to East Asia, and the cold tongue is also stronger. So this is one way that we can track differences between El Niño and La Niña. And in the satellite image over here of sea surface temperature anomaly, this is now a recap of that last video we saw, where the anomaly of El Nino is going to be given by this warm water tongue, whereas La Nina is going to be colder because the trade winds are stronger. And so the upwelling of the cold water from the interior is more extreme. And going between these two different phases of warm and cold surface temperature anomaly, this can give us basically this index that you're going to be computing in today's tutorial, which can track the differences between El Nino and La Nina phases using sea surface temperature in the Niño 3.4 index.